So we are on section 4.2. We're going to deal with probability rules. And there are lots of different situations that are going on here, so I'm trying to cover as many as I can. Some come from tables, where you just basically get the relative frequency, and use that as your probability. And then others, we get it using theory. So I'm going to jump right into a kind of overlap question. Let's just remind you of the deck of cards. So we're going to do a lot of questions on using decks of cards. You can have hearts, diamonds. I know that most of you know exactly what this is, but not everybody actually does cards, I guess. Hearts and diamonds are red in colour, and then we have spades and clubs, and they're both black in colour. And all of them start with an ace, and you go 1, 2, 3, all the way up to 10, and then the last three cards called Jack, Queens, and Kings. These things at the end, these are all called face cards. So we're going to look at two distinctly different kinds of questions. They might seem that they're the same, but they're not. So situation 1 is going to be a single card story. So in these stories, you're being told that you deal a single card from a deck of cards, and you're being asked to calculate various probabilities, depends on what the story is. So I'll start off with the simplest situation. You could just be asked, what's the probability that you choose one card and it's a heart? Well, these are all theoretical. You don't actually need to get a deck of cards and see what happens. That would take you far too long. What you basically do is you do counting. We know that in a normal deck of cards, there are 52. There's basically 13 hearts, 13 diamonds, 13 spades, and 13 clubs, right? So there are 52. And 13 of them are hearts. And as a decimal, 25%, 0.25. So that's a single card question. Then you go and you do a question like this. What's the probability that you choose one card again, but this time you choose an ace or a king? Now, in this particular question, you can also do it by counting. In a normal deck, there are 4 aces. Add to that the 4 kings. That ends up being 8 over 52. And that turns into about 0.15. I'm doing all my questions to 2 decimal places. But, you know, check the homework. Sometimes it's 2, sometimes it's 3, sometimes it might even be 4. Then I'll try this one. You choose a single card from a deck of cards, and you get an ace or a red card. Okay, now it's a matter of counting, but you've got to be careful here. There are 4 aces, agreed? 4 different aces. How many red cards are there in a deck of cards?
$26.
There it is. And now, that's not the correct answer, is it? Because haven't we counted some cards twice? And so you need to take away, and I'm just going to call it both right now. That's going to turn into a number in a second. I'm just calling it both. So how many of those cards are red aces, right? They're both things. How many red aces? How many are both things?
Is it 2?
Yes. And so that guy, when you get it, becomes 28 over 52. And 28 divided by 52 ends up happening quite a lot of times. In fact, about 54% of the time. So if you're hoping for an ace or a red card for whatever reason you want that, you're going to be successful, right? The probability is that about 54% of the time, that next card, the one you want, will be an ace or a red card. Now, what's the difference between this ace or king and this ace or red? Well, in this top one, aren't aces and kings totally separate? And that's why just adding them together worked. In this case, don't aces and red cards share some components, right? There's some cards that are red aces. And we introduced a term on Tuesday that describes this, and that term is called mutually exclusive. So two things, in this case ace and kings, are mutually exclusive if they do not share any, well, what would you call them, events. So they don't share anything. And if they are mutually exclusive, you can add them this way. And if you stick the word not in front of it, so they're not mutually exclusive, that's if they do share some common events. So what you have to worry about or look for is if you ever get an ace or king kind of question, that you got to say, am I going to have to deal with this subtract 2 situation, or will I simply just be able to add them together and it's fine? Now we're going to look at conditional probability. So conditional probability is basically if you know something is true, if you've got an extra bit of information, it can change the probability of an event happening. And so, again, we're still on a single card question. I'm going to do this version again. A face card is a jack, queen, or king. In a normal deck, there are 10 cards that are called face cards, right? There's 3 hearts, 3 diamond face cards, 3 spades, and 3 clubs. Now, if I ask you, what's the probability that you get a king? And I don't say anything else except that, then it's 4 out of 52. It's a very small probability of happening. So 4 divided by 52, it's about 8% if you round it off to 2 decimal places. But you will sometimes be asked to find what's the probability that you get a king given, oops, that's what that line is, that it's a face card. So that vertical line is used to represent the word given. So if I was reading this out, which I was, the probability that you get a king, given that you already know it's a face card. So imagine by whatever it means Somehow you caught a glimpse of the card and you knew it's a face card. You couldn't see a lot to tell what else, but you knew it was a face card. The world now changes. Since you know it's a face card, there's only 12 face cards in the deck, so it must be one of those 12. Do you see that the bottom number has changed? Now, how many of those 12 cards are kings? So if you go through the deck of cards, how many of those cards, those 12, are kings? I need some help here. It's not meant to be a trick question. Look at a deck of cards. How many kings have they got?
4, right? Is it 4?
Yeah, it's 4. Well, you're thinking I was trying to be sneaky and give you a question that wasn't as straightforward as that. Right. But if you do this guy, can you trust me that it's 33? That's what 4 out of 12 gives you. What does that tell me? It says, well, if I don't know anything, the chance that I get a king is 8%. But if somehow I knew it was a face card, the chances that it's now a king has increased by a lot. Try another one of those then. What's the probability that you get a king given that you knew it was a red card? Now, since you've been told that it is definitely a red card, right? That's for sure. When you go through the deck of cards, there are 13 red hearts and 13 red diamonds. So the world is now 26, which means that only those 2 rows matter now, because they're the only 2 that can exist. So here goes. How many kings are there now?
2.
Yeah. And that guy comes out as a really ugly fraction, as pretty much all of them are. And that's about 4%. Well, let's just look at a king on its own is about 8%. If I tell you it's a face card, your chances have grown to 33%. And if I tell you it's a red card, actually get checked that. Yeah, it's changed again. Oh, here's a silly one. This is a trick question. I'm warning you right now. This is a sneaky question. What's the probability that that card is a king, given that you know it's definitely an ace?
None.
Yeah. None. So it's a kind of trick question there. Do you see in that case, another trick question I could have given you is, if I told you it was a king, wouldn't that be a probability of 1 then, right? So these things called conditional probabilities are probabilities where you know, you've been asked to find something, but you know a piece of information that's going to alter that probability. The information that you've given can sometimes make it easier to get the probability that you want, right? That's bigger numbers. It can also make it 0 or even smaller than what it would have been. So some information makes something more likely. Some information can make it less likely or even impossible. So I'm now going to continue with kind of single thing happenings, but I'm going to leave cards for a while, and we're going to do a table. And we're going to put this table into young, and old. And we're going to put it into Republicans, Democrats, and independents. So someone goes out and they collect information about how people vote, whether they consider themselves a Republican, a Democrat, or an independent. And they also record, and it's quite arbitrary in a way, who are young and who are old. So you could say, and I'm making this top of my head, if you're under 30, you're young. If you're over that age, then you're old, right? So I guess they asked them their age as well. And this is the kind of numbers that we got. And I am making no assumptions that this is true data. This is pretty much random numbers that I put in, right? So the real numbers could easily be totally different from that. So don't take any offense or whatever from this. Now, from a table like this, there is a number of different probabilities that you can get. All my probabilities are going to start with this sentence, so I don't have to write it every time. You choose one person at random from this poll. And here's my first question, and you choose one person at random from this poll. What's the probability that you choose a Democrat? Now, we know that probabilities are fractions, right? We have a top number to get and a bottom. This is not coming from theory, right? It's not like I know how many cards in a deck, but the information is still there. Shouldn't the bottom number in this story be the total number of people, right? I mean, who could I pick? Well, I could pick any of them, I guess, right? That's the bottom number. So I'm going to put little totals in here so it's easier for me to keep track of them for later. If you add that top row up, you asked in total 110 young people. And on the bottom, you asked 90. Oh, I got kind of lucky here. Now, if you go down the way, there's 70 of these, there's 70 of these, and there's 60 of these. So the question was, what's the probability that you chose one person at random from this poll and they were a Democrat? Well, there's 200 people you could have picked, right? And out of those, 70 were Democrats. So the probability then that you did that is 70 divided by 200, and that is 35%, right? There's a 35% chance you chose a Democrat. Suppose I said, what's the chance that you chose an independent? Well, aren't there 60 independents, but you could have chosen them out of any one of the 200, and that's a little bit less, about 30%. Are we cool with that? What's the probability that you chose someone who was young? Well, there's 200 people you could have chosen, and do you see that 110 of them are young? So that's what, about 55% chance that if you chose one person at random from this poll, they would be young. Those are pretty straightforward counting questions, right? So what I'm going to now do is make them harder by giving you a conditional probability. So what's the probability that you choose a person at random and that they're a Democrat, given that they were young? So you know that they're young. What's the chances that that person you chose was a Democrat? So what you have to do is you have to go over to this table and you have to say, okay, since I know that they're young, doesn't the world only consist of that top row of the table now? right? Since you know they're young, it has to be one of those 110 people. That makes sense. Now, out of that 110 people, there's 40 Democrats that you might have picked. 40 out of 110. And the answer here is about 36% chance. It's a probability that you choose a Republican, given that it was young. Well, there's still 110 young people, but there was only 20 Republicans. And in that case, it's only 18%. Now, it's from questions like this that you can start actually making some assumptions. Can we just pretend that this is some other country in the world, right? So I'm not getting into politics, I just like the numbers. That in this other country in the world just happens to have Republican, Democrats and independents. Based on this one, wouldn't it be reasonable to say that young people vote more likely to vote Democrat than Republican? Do you see, just looking at these two, does that seem a reasonable conclusion? Right? That young people, in fact, roughly twice as many are likely, right? Twice as likely to have. Okay, let's try a different one. What's the probability that you do Democrat given that you're an older person? And let's do the probability that you vote Republican given that you're an older person. And in this case, then, won't the world change a little bit? Since you're told that it was an older person, do you see the world now is that bottom row? And so there's only 90 people to choose from, 30 who are Democrat, that's 33%. And in this one, there are 90, but 50 of them are said they were Republican, so 50 divided by 90, I get about 56%. So when I look at this data, what this is telling me is if I was interested in how young and old people vote, couldn't I say that the Democrats are doing better with young people and the Republicans are doing better with older people? That's an interesting piece of information. Now, how about this? I already know that the probability that you are a Democrat given that you're young, we already calculated that one. It's 0.36. Let's switch places. This probability is not the same as that. I know they use the same two terms, but this is, what's the chance that you're a Democrat given that you already know it's a young person? And this one is, what's the probability that you're a young person given that you're known a Democrat? Well, let's see what that one looks like. Since you're told that they're a Democrat, doesn't the world now become that single column? So there's only 70 people who are Democrats. So if you're told it's a Democrat, it's those 70 that you're dealing with. So there's the bottom number, goes there. And of those 70, right, how many of them are young? Well, the top number is the young ones. So the answer is 40. And what we have here is 40 divided by 70. And this here is 57. Now, if being young and Democrat were independent of each other, in other words, it didn't matter if you were young or old, whether you voted Democrat or not, right? It had no effect on it. If that had been the case, these two numbers would be the same. So if you want to test, are two things independent, right? They don't affect each other. Find these two different conditional probabilities. If the numbers end up being the same number, then you can say that they are independent, right? being young doesn't really affect your thing. Can you imagine I did a table where I got blonde-haired people and red-haired people, and I found out how they voted? Can you imagine that a blonde-haired person doesn't vote any more or less Democrat than any other coloured hair person would do? So the colour of your hair would not would be independent of how you voted. And that's how you can test for independence. You find two conditional probabilities. Okay. Do we have any questions about this so far? Are we good? Last chance? Okay, I'll assume that this went fine. So, let's move on and do not single card questions, but two card questions. Now, in these questions, it's going to start with this same sentence that I'm not going to do except the first time. You take two cards from a deck of cards. What's the probability that, say, both of them are kings? Now, when you have a two-card situation, you are going to be multiplying two probabilities together. And the two probabilities you're going to be doing in this question is the probability that the first card is a king multiplied by the probability that the second card is a king. And this is where it gets a little bit subtle. Okay, imagine you've physically got the cards, you're giving them a shuffle, and you're turning the first card over, up. What's the probability of that first card being a king? Well, there are 52 cards, and 4 of them are kings. Check. Now, the second card also has to be a king, right? Because there's 2 kings. Second card has to be a king. How many cards are in my deck? Because I've already put the first king down and it's on the table.
51.
Right. And of those 51, how many of them are kings? 3. Do you see in this case the 2 things that are multiplied together are different because one has affected the other? So in this case, you just multiply them together. Pretty horrible calculation, but I can do it. 12 divided by 52 times 51. And the answer I get, I'll have to do it to 3 decimal places or you won't even see it. It's that guy, which is about 0.5%. So if you were playing cards and you just randomly gave them a good shuffle and you turned 2 cards over, do you know 1 in 200 times you'd probably turn over 2 kings? So can you imagine 2 kings is a pretty hard hand to get? Right. What's a different one? What's the probability that the first card is a king and the second card is an ace? Which is actually a really good hand in blackjack, right? That's 21. You're going to win. I wonder how hard that is to get a king the first time and then get an ace the second card. Well, there are 4 kings out of 52. Nothing really changed with that one. Now, the first card is down on the table. It is a king. We know that is done. Let's work on what the second card has to be. Would you agree there's still 51 cards? How many of them are aces. Agreed? All 4. Now, that gets you 16 divided by 52 times 51. And that gets you 0.006, which is 0.6%. That might surprise you. Do you know it's harder to get 2 kings than it is to get an ace and a king? 0.5%, 0.6. Now, if you were a gambling person, wouldn't that might be to your advantage to know getting an ace and kings a little bit easier than getting 2 kings? It might adjust how you would play the game. Are we good? Let's make it a little bit harder. What's the probability that the first card is red and the second card is black? That's nice and vague. First card is red, second card is black. Okay. First card, 52 cards to pick from. How many of those cards are red? How many
Is
red?
it 26?
It is, thank you. Now, just like we did before, can you imagine that card is now down on the table and it's a red one? Can you see that the second card, there's only 51 to pick from? But aren't there still 26 black cards because you never ate one of them up? Now, I'm doing that calculation, which is pretty messy as well. So I'm going 26 times 26, got that. Divided by 52, got that. Divided by 51, got that. And that is going to happen 0.255, or about 25.5% of the time. A little bit more than a quarter of the time, you're going to get a red and a black. Okay, let's go for glory then. This isn't a 2-card question. This is going to be a 4-card question. What's the probability that you get a heart, another heart, a 4th heart? Actually, I'll make it a 5-heart question. Right. What's the probability you get dealt 5 cards and every single one of them's a heart? That's called a flush in poker. Right? So if you get dealt 5 cards and they're all hearts, let's see how that one works. Well, based on the 2-card deal, would you agree this is probably just going to be 5 multiplications rather than 2? And it's going to go first guy, second guy, third guy, fourth guy, last guy. We'll start with the first one. It has to be a heart. There's 13 of them, and there's 52 cards. Well, the first time there is. Right. What bottom number goes in the bottom when we deal with the second card then?
51.
Have you noticed that you're eating one up? How many of those 51 cards are hearts?
12.
12. Because haven't we eaten a heart up as well? So we've done 2. On to the third one. There's 50 cards left, but won't 11 of them be hearts? Then there's 49 cards, and there's 10 of those. And then finally there's 48, but there's only 9 of those. Now, that kind of calculation is going to screw up your poor calculator no end. And it's quite hard to do correctly. And so I'm going to show you the slow way, but at least I know it works. If you try and do it some of the other ways, the numbers are so big, your calculator just kind of goes wonky on you. So I just put brackets around everything to be safe. And I go 13 divided by 52, close the brackets, and then go times. And then I do another bracket with 12 divided by 51. Then I go times, another bracket, and I do 11 divided by 50. Then I go times, I'm almost there. Another bracket, 10 divided by 49 times, and one last bracket, 9 divided by 48. It's a bit cumbersome, but when I hit enter, I get the right answer. Now you might say, whoa, that doesn't look like the right answer. I'm just going to write down the first few digits and then this funny little guy, e to the negative 4. Does anybody know what the calculator's trying to tell me when it does an e to the negative 4? Because it is trying to tell me something.
Move the decimal place 4 spots to the left.
Do you see how tiny, how hard it is to be dealt 5 cards, one after the other, and they're all hearts? We'll assume that nobody's cheated and the cards are well, decks well shuffled and so on. That is going to happen very rarely. So if you were ever playing a game where they dealt you out 5 cards and they're all hearts, I wouldn't say bet the house on it because, you know, maybe somebody else got a really lucky day and beat you. But wouldn't there be a good chance you'd at least bet your car on it, right? Now, if that had been a really high number, well, that means a lot of people could be getting it, not just you. But such a small number like that means it's a very rare event. Okay. Now, one last one of these. I'm trying to think of a poker hand that's kind of impressive. How about 4 aces? Would you agree? I mean, if you see it in movies, the guy has 4 aces. Yeah, and that's pretty much it, right? So I wonder what the probability of a 4 aces is. Four multiplications. Gut feeling. Do you think it's easier or harder to get 4 aces than it was to get 5 hearts?
Harder.
Harder.
Let's find out. I agree. That's what I would think. Right, first card. 4 aces, right? Out of 52. Second card. Third card. Last card. If you do enough of these, and I wish we had time, we could do tons more, but do you see there's a kind of pattern to what's happening? In particular, do you notice that you always reduce the bottom number by 1 in these kind of questions? Because every time you do another card, that assumes you've used up 1, right? And don't the top numbers, depending on the story, don't they very often change as well? Depending on what the previous thing is. Now, that particular guy is, here it goes. .69 e to the negative 6. It's almost getting to the point where it's ridiculous. Very, very roughly, this is 100 times harder to get than that. Now, getting 5 hearts, getting a flush, is remarkably rare. But getting 4 aces, right off the bat, right dealt to you, 4 aces. Actually, what's the chances of getting 4 fives? I don't need to do another calculation. What's the probability of getting 4 fives?
Isn't it the same?
It is. And 4 queens, and 4 tens, and 4 anythings. And see how I did 5 hearts up there? Wouldn't 5 clubs be the same? Wouldn't that be the probability of getting 5 clubs? Or 5 diamonds, or 5 spades? Are we good? 1 card, 2 cards, multiple cards. Conditional probabilities. right? And some tables. Let's go and have a look at some of the questions from the homework then and see what that looks like. I have a chat here. What's going on? Right, Beckton says he can't hear anything. Do you hear things now, Beckton?
Yeah, I can. That was a while.
Okay, so it must have been your end then. Okay, and let's go in. We are done. We are in, not done. Okay, let's get by some of the earlier stuff and go to some of the guys I've been doing. Okay, here's question 10. You might or might not know that M&M candies come in various colours. And this is, allegedly, I'm assuming it's true, the percentage, pardon me, of each colour that you would typically get in a bag of M&Ms. For instance, did you know that red is the most common number? There's 23% of them are red. And that orange, there's only 6%. So there's roughly 4 times as many red M&Ms as there are oranges. Okay. Now we are going to find out some probabilities here. Now, in this particular case, we're being asked to do, well, let's just say, find the probability that it's a green candy or a blue candy. Well, there's 7 of them are green, right? And 9 of them are that. Your homework couldn't be much easier than 16. I've tried to put percentages in and it never seems to like it. Oh, go figure. It does like it, 16% today. Now, it says, are these events mutually exclusive? Is a red candy and a blue candy mutually exclusive? They don't share anything. You're a bit quiet, so I'm not sure what you said, but hopefully you were talking about this question. Are green and blue candies what we call mutually exclusive? Is it yes or no?
Yes.
Correct. So choosing a green and blue M&M is not possible. That's why. They give you another yes, it's not correct. And the same one there. Oh, here's one. Not purple. Well, I could do it 2 ways. If I was being just, not thinking too much, couldn't I just add up all those guys? Or, if you're not purple, aren't you the other 79%? If 21% are purple, aren't the rest not purple? And that's me using the complement trick. Question 12, you roll 2 dice. One is green and the other is red. Oh, that's nice. Red dice, green dice. Are the outcomes of the dice independent? Does the number that turn up on one dice affect what's going to happen on the second? And if they have no effect on each other, we say, yes, they are independent. Independent means one doesn't affect the other. Right? Now, find the probability that you get a 5 on the green and a 1 on the red, and they want your answer to be a fraction. Oh, cool. Well, my thing doesn't do the little thing, but yours will. What's the chance of getting a green 5? Isn't it 1 out of 6? What's the chance of getting a red 1? Isn't that also 1 out of 6? So if you were doing that as a fraction, it would be 1 out of 36. Okay, that's what that question is about. 13 is very similar, but it's to do with dice. Okay. What's the probability that you throw a dice and you get a sum of 6? I think we did that on Tuesday. So you remember you throw 2 dice and you add them together? Can anybody remember what the bottom number was? How many different things happen when you can throw 2 dice? Right, 6 numbers on the red dice. 6 numbers could happen on the green dice. How many different combinations of those could happen?
Isn't it 36?
It is 36. Now, top number. I guess I would probably use my fingers. So here goes. If you want to get a total of 6, couldn't you get a 5 and a 1, a 4 and a 2, a 2 and a 4, and a 1 and a 5? So there's 4 of them. Is that right? 5, 1. Oh, forgot 3 and 3. There's 5 of them. And we kind of tackled that last time, so that's what these are. And here is another question to do with 2 dice, so I can hopefully get by that. Question 16 is to do with doing cards, right? We've covered those. So getting a first card is a 10 and a 10 on the second. So that's, you know, first guy times second guy situation. Here's another card game. Here's another card game. So you know the 2 probability things, that's what's going on here. Let's look at question 20 now. Okay, here we have a table. What's the probability that a toy is purchased from someone in the following age group? 12 years or younger. Well, if you want to get 12 years or younger, aren't you basically going to add up everybody in this set here? So 11, 26, 17, and 15. Now I could get that answer by adding those together, right? That would be younger than 12. Is there a quicker way of doing that in your head so you don't even need it? Logan?
31 minus 100.
Right, it's as simple as that, isn't it? Just 69. That's using the complement trick, right? Now, this one here, I'm going to take a copy of, that way I can go back to our paper, because there's a lot of stuff going on here. This is some data collected on sales effectiveness. So I guess you go to a seminar and they tell you strategies for selling things. And here goes. I need some color schemes, I think, here. 261, 319, 478, 102, and some totals, and then we'll be ready for the question. 580. Oh, 580. $739 and $421. Right, so we are going to look at this data and we're going to use it to, okay, where are you? Here we go. We're going to look at it and calculate some probabilities and then maybe some conclusions about good strategies for a salesman. Let's just look at a simple probability. What's the probability? Oops, I forgot the total here as well. So 0, 6, 1160. So what they did here is they got 1,160 people, That's a lot of people in the sample. And they looked at their strategies. And let's talk about some of the numbers first. 261 people got a sale when they were doing aggressive selling. You know, like I don't know if your experience is anything like mine, but I don't like going to used car sales places to get my next car. I call them vultures. They kind of circle round. And then you know what happens when you come in, aren't they? Oh, some of them are quite aggressive, right? They come over and, what kind of car would you like? I know a really good car that would suit you. And, you know, they're pushing, right? They're trying to get a sale, obviously. That doesn't work well with me. If someone's too pushy like that, I tend to just leave and go to some other place because I don't like feeling that I'm being forced into anything. Just my personality doesn't work well. Now, in that situation, can you see that when they were aggressive, 319 of them didn't get a sale? And here we've got passive and so on. So what's the probability? Let's just do a simple one. That actually anybody managed to sell something, right? They got a sale. Well, there's 1,160 people here. And out of that 1,160, 739 of them did get to sell a car. So 739 divided by 1160, it's about 0.64. So that's what, a 64% sales. I'm not going to calculate this one, but I know the answer. What percentage of people didn't manage to sell anything? 64%, right? 0.64 did sell something. So what's this guy? I don't need to do any calculations. Can't I do it in my head? I'm pointing this. That's it. I see your lips moving. It's 36. If you're not sure where that's coming from, aren't both of those the only things that could happen? You either sell it or you don't. And isn't there a rule that says those two always add up to 100%? Right, let's do a conditional probability. What's the probability that you get a sale given that you were aggressive, right? So you're an aggressive salesman. What's the chances that that type of sales strategy actually ended up in a sale? Now, in this world, you're told that they are aggressive. So doesn't that mean that the data now means that only that row matters? If you're told that someone's aggressive, right, that's a given, then the information comes from the top row. And in this case, 580 and 261 was a sale. So 261 divided by 580, they got a 45% sale rate. Let's compare it against the alternate choice. Well, if you are passive, right, you're not pushy, that would be another way of saying it. Do you see that you now belong to the bottom row? Passive. And of those, there was 580 and 478. And according to this, 478 divided by 580 ends up being about 0.82. When I look at these two numbers, then I think there's evidence to prove that actually, if you want to sell something, it's much better not to be pushy, right? Not to be trying to sell someone, you know, the hard sell, according to this data. Now, if this data was, maybe it's not accurate, that's possible. But that's what the conclusion I would make from this. Now, if I tell you that the probability that you get a sale was 0.64, and the probability that you get a sale given that you were not pushy, you were passive, was 0.82. These two numbers are not the same. Agreed? Doesn't that mean that sales, whether you get a sale or not, and being passive, they are not independent, which we call dependent? That is evidence to say that it does matter, right? If these two numbers are equal, then it means they are not connected, right? They do not affect each other in any meaningful way. So imagine I went and said, suppose we collected data on whether you got a sale or a no sale, and we just used whether you had blonde hair or black hair, right? Can you imagine in those two situations, I don't think that has any effect. Then these two numbers would be the same number. They wouldn't be 0.5, right? They could both be 0.2 or both be 0.9. What I'm saying is that they're both equal to each other. And that is a way that we can test, are two things connected? Do they affect each other? Find the probability of whether it is on its own. Find the probability of whether it is given the other variable has happened, whatever that other thing is. If the two probabilities are equal, you know that these two things are independent, they don't affect each other. If they are different, then you do have evidence that they are affecting each other. In fact, if these two numbers are wildly different, it means that these two things are very heavily connected, right? They change each other really a lot. And if these two numbers are almost the same, it means that they are dependent, but nothing that big, right? It might make a 2% difference to how many sales you get, right? So maybe somebody who has a really good, smart suit on might get 2% more sales than somebody who's a little bit too casual, perhaps. Do we have any questions about that particular group of questions? We feel good? Okay, I'll move on. Next, Philip, can I unmute you? I guess I could. I think I've unmuted you. Will someone talk without putting their hand in the space bar to see if I've done it?
You didn't unmute.
I didn't. Darn it. Okay, evidently I got one shot to do it and then I can't undo it. I guess I could do it this way.
There. They just have to accept it.
Yeah, so if you accept it, then I can unmute you. It's a bit slow, but that's fine. I'm not sure I want to do it now. You can't win because we get background sounds and that distracts people. So, okay. Those who feel comfortable about unmuting, do it. If you don't, just mute yourself back in again. Okay, now I am going to do another one of those table questions. We're going to do a fictitious story. At least fictitious in the sense that the data I'm giving you is made up, but the idea is not fictitious. Let's do tests for HIV. So, you collect data on how successful a test is. By that we mean, does it do what it's meant to do? So let's suppose we have an HIV test. And there are a number of things that can happen, right? You can test positive, or you can test negative. So in the medical world, testing positive means you took the HIV test and it came back and says, we think you've got HIV. Or you take the test and it comes back and you say negative. Now that could be the COVID thing, right? You take a test. You know, not all tests are completely perfect. And if anyone ever tells you they're just lying. I'm sure the COVID test is not perfect either. There are a number of reasons. It doesn't mean the test is bad. It's very successful and it does what it does. But you know, if someone has just caught COVID, like they caught it 10 minutes ago, kind of caught it. Do you know you'll have so few antibodies in your system that the test would never be able to find it? Can you understand that can happen, right? So in HIV, if you just newly acquired that, can you imagine that the test might not pick it up yet because you don't have the signature that it needs? Now, the other side is you actually do have HIV, or you don't have it, right? So let's put some numbers in here. You test positive and you do have it, and we found out that that was 900 people. Tested positive and they did have HIV, right? They discovered, you know, later on they had all the things that make you have it. Now, you have HIV, but you tested negative. And that ended up being, let's pretend in this test, 100. Now, you don't have the test, but you test positive. In this case, 200 people tested positive for HIV, but later on they discovered that it was just a peculiarity of their blood system and it wasn't, you weren't. And we're keeping this data kind of symmetric. 800 people don't have the test and they tested negative, right? So what we're going to do is we're going to use this table, and I've kind of made the numbers, at least in one direction, nice, in the other direction a little bit skewed, but that's okay. We're going to use this to look at some probabilities that are useful. Let's introduce you to some terms that you may know. There's a term in medicine called false positive. You heard that term? That was a false positive. Now, I know some of you, at least some of my other class are, and hopefully some of you are in the medical field. What is false positive? What does it mean?
When you get a positive result and it's not correct.
Okay, so in this case, that would be the probability that you tested positive, right? Given you don't have HIV. That's how false positive would work as a probability, right? What's the probability that you tested positive given that you don't have HIV, right? That's a false positive. So let's find out what that percentage is, which we can get from this table. Now, since I tell you you don't have HIV, do you see that the world now only exists as the bottom row? And when we look at that, 200 tested positive, right? 200 tested positive out of 1,000 people. And that is that guy, and I'm going to convert it to percentages. That is a 20% false positive. Now, when HIV first came onto the scene and they were trying to, you know, one of the things that they tried very quickly is, we need a test to see if you've got it. Do you know some of the early tests were pretty bad? By that I mean they weren't very good at doing their job, right? 20% false positives is pretty high. I don't want to get tested for COVID and they tell me I've got it, and then 20% of the people they tell they've got it actually are totally fine, right? That would cause all sorts of havoc. I mean, it would fill up the hospitals for starters, wouldn't it? You'd end up in the hospital with a whole load of people who don't need to be there because they didn't have it in the first place. Well, there is another version of that. And that's called a false negative. So let's see what that looks like. Well, wouldn't that be kind of the other way around? You tested negative for HIV, but you really did have it. So let's see what that looks like. Well, the probability then that you tested negative, given that you, I guess I'll abbreviate it, that you do have HIV. Now, since you do have HIV, do you see that the top row looks like that? And the people who tested negative in that world, well, there's 1,000 people and 100 of them, and that ends up being 10%. Now, both of these are actually errors, right? They are mistakes. You said something that wasn't true. Here, 20% of the people you said tested positive, right? 20% of the people you said had HIV didn't. And here, 10% of the people who you tested who said they didn't have it ended up having it. And now you have to bring into effect value judgments here. Yes, that's the word I'm trying to look for. Both of these are mistakes, they are errors. One of these, in my opinion, is a worse error than the other. By that I mean, it's more likely to cause a lot more problems than the other error is. Which one of the two do you think, I think, is the worst mistake to make?
The probability test of false positive.
Do you think a false positive is severe? I know it's bigger, but we're not talking about big now. We're talking about value judgment. Which one is worse?
Well, I'd say the false negative is technically
Yeah.
worse because more people are walking around.
That's the one I was getting at, yeah. Because think about it. If it's you, hopefully it never will be, but if it was you, if you tested negative, a couple of consequences. Isn't the first one you don't go for treatment because there's no treatment because you didn't think you had it? So won't the disease get worse? Whatever that disease is, right? Secondly, for a test like this, or for a situation like this, couldn't you, since you believe that you were okay, couldn't you have behaviours that lend yourself to being in more danger, or your partner being in more danger? Because you'd think there's nothing, I don't have any illness, I'm fine. Now, there is problems with that top one. The first one is, that's going to scare you, right? Because the doctor's going to give you that phone call. Well, your tests are just in. You've tested positive. I'd like you to come in tomorrow. We're going to do some more tests, right? We're going to make sure that it's right. And you're going to have a lot of time worrying about this, and then eventually, hopefully, going in and, you know, they do other more detailed examination, and that comes out. Now, if this and this work, what you've got is a problem with balance. And you say, well, what do I mean by balance? If you imagine you've got, at one side, you've got all the false positives, and at the other side, you've got all the negatives. If you make a test so severe that you never get a false negative, you are going to guarantee to increase the false positives. Right. I'll do a trivial example. Suppose I just said to every single person who came to get a test, yes, you've got HIV. Won't I be 100% correct for those patients who did have HIV? So won't the false negatives be zero? Won't the false positives be through the roof? Right, because everybody came and I told them that they were off. Now, what does that have an effect? Well, there's a limited amount of hospital beds. There's a limited number of doctors and time. Can't you don't you have to make a judgment call about where you want your test to be? And mostly what happens in these tests is there's something that they measure, and if it's bigger than this number, you've got it, and if it's less than this number, you don't. That's a very primitive test, but a lot of tests can do that. You have a big problem when you do something along these lines. We want this to be as small as possible, just for the sheer dangers that it causes those people. But there's a balance at the other side. I have no idea how people decide that, but evidently they have ways to do it. All right, do we have any questions about that? Are we good? Right, so I'm going to, again, I'm jumping around a lot here today. I'm going to go back to the homework. There's two more things I need to show you. And then I'll be happy. Here's one of these false positive, false negative questions that I've just did. So this one is question 22. Here's another false positive, false negative. This is question 23. And here's another one, question 24. These questions are really important. That's why you're getting plenty of practice at them. If you're in the medical world, you want to know a little bit about how do they calculate these things and how important are these results. Question 25 is really just a big version of the tables that I've done. So that's one of the two things I want to cover. I hope that you can get plenty of practice at doing these false positive probabilities, false negatives. And then up the top somewhere, if I can find it, we got a couple of questions to do with probabilities, mutually exclusive and independence, and what else? And complements. Okay. So here we go, question 7. Suppose two events A and B are independent and the probability of A and B are not 0. By working through the following steps, you'll see why two events are not mutually exclusive. What formula is used to compute A given B? So they're telling you what you're going to do. If A and B are independent, which one of these 4 formulas will get you the probability that A and then B happens? If they are independent, which one do you get? A and B. The first dice is a 5, the second dice is a 7, that kind of question.
Just add.
If it's not add, what else might it be then?
Multiply.
Yes. You do combine them by multiplying. Oh, so when's the add going to happen? If it says A or B, you'll add. And if it's A and B, you'll multiply. So that's how you tell the difference, right? So what's the probability? Is A or B, you're adding some things. A and B, you're multiplying some things. It says, is the probability of A and B not equal to 0? And the answer is yes. And the result was that one. On to question 8 then. Consider these two events. A, the driver is under 25, and B, the driver had a speeding ticket. Here is a probability in English, and our job is to convert it into one of these guys here. So, what's the probability that the driver has received a speeding ticket and is under 25? Well, the minute I saw this word and, that took me right to there. And none of the others even have it, so I'm just going to call it that one and move on. The probability a driver who's under 25 has received a speed, that's the same question. Oh, almost the same question. the probability of a driver who is under 25 years old has received a speeding ticket. Now, if you tell me that he is under 25 years old, haven't you told me A? So I am looking for a conditional probability, so that makes it this one. So you're going to take these sentences and they're going to end up being one of these calculations down here, and then another batch, the same practice. So pick one at random. What's the probability that a female student is majoring in business? Well, you know they're a female student, so that means it's given. And I got up here, and A means you're a female student, so it must be that one. So hopefully you'll have plenty of